Namaste everyone. We are moving into our second lesson in current electricity, and today, as you see on your board, we will be discussing about Ohm's law, and we are going to try and derive Ohm's law, and we are going to use it to relate resistance and resistivity with relaxation time. I hope you have seen the first video and you are aware of what is meant by relaxation time, and we are going to denote relaxation time by tau, the time interval between two successive collisions of electrons when applied, when they are moving in an applied electric field. Okay, so let's begin with our first part, that is to recall Ohm's law and then hence to derive Ohm's law. So if you look at Ohm's law, which you have studied in your lower classes, the potential difference across the ends of the conductor is proportional to the current flowing through it. So that's what we are going to say. But the condition that we are imposing on the current to remain a constant is, the current to be proportional to the potential difference is you have to keep certain physical quantities a constant. In lower classes, you would have been only told about the temperature being a constant. Now we are going to say that even the pressure applied or the strain that the wire is subjected to should remain a constant. The conductor is subjected to should remain a constant for Ohm's law to be obeyed by the conductor. So if I'm going to put it mathematically, I have V proportional to I. The potential difference across the ends is denoted by V, and it is going to be proportional to the current flowing through it. So V is going to be proportional to I. And again, in lower classes, you have been told that the proportionality constant that we are going to introduce is called R, where R is nothing but the resistance, electrical resistance offered by the, so R is the electrical resistance offered by the conductor. Is that clear? So that is what you have studied. So this has to be recalled, and I hope many of you would not have forgotten it because you have done it again, again and again and again in grade 10. And what we are going to do now is to try and derive an expression for resistance using what we have done in the previous class. So in the previous class, if you see, we defined something called as VD, the drift velocity of an electron, that is the velocity with which electrons are going to move in the presence of an electric field when the conductor is connected to the source of an EMF. Right now, I know that it is going to be minus E by m into tau, if I'm going to write it in vector notation, because the electrons are going to drift in a direction opposite to the direction of the applied electric field. We have a negative sign. Now, what if I'm going to consider only the magnitude of the drift velocity? Then I have Vd is equal to E by m into tau. Now let us assume that this this electric field produces a potential difference of V across the length L of a conductor. So let us assume the conductor having a potential difference L across its length L. Then what can I say about E? E is nothing but, again, if I'm going to consider only the magnitude, I'm going to write my E as capital V by L, because E is equal to minus dV by dr in vector notation. So in magnitude, it is nothing but the potential gradient, that is V by L. So I have my Vd to be equal to E by m tau, where here tau is our relaxation time, that into V by L. Isn't that clear, children? Now what am I going to do? We also derived the relationship between current and drift velocity. And what did we write that as? We wrote it as NAEVD. Again, please, if you have not watched the previous video, go back and watch and then come back to this video. Otherwise, you're not going to follow what I'm saying now. So the current flowing through the conductor in the presence of an electric field is going to be given by NAE into VD. Now, what are we going to do? We are going to simply substitute for this VD from the above equation. So what am I ending up with? I have my I is equal to NAE into VD के बदले में E by m tau into V by L. This is what we have substituted for VD. Now from this equation, what am I going to write? I am going to write V by I. This implies. So I goes this side, all the other factors are going to come up over here. So what am I going to end up getting? I get ml. So this ml comes over here and I have NaE square tau. Isn't that correct, children? Just pause a while and see if this is what we have. NaE square tau, while ml comes in the numerator, V by I. Now watch the right hand side of the equation very carefully. What do we have? We have m here. M is nothing but, if I'm going to give a subscript to it, it is nothing but me, the mass of the electron. And what is L? The length of the conductor through which it is flowing. And what is N here? N is the charge density of the given material of the conductor, which is not going to change under normal conditions. So that remains a constant. Capital A, the area of cross section of the wire, that is also going to remain constant under the given experimental conditions. And then E, charge on an electron. Tau, the relaxation time, it is the average relaxation time for a given electric field in a given conductor. So if you look at the right hand side, we see that under conditions that are maintained during the experiment, the quantity on the right hand side remains a constant. That means this expression implies V by I is a constant. Right? That is what Ohm said. And he said this constant is nothing but the resistance offered by the conductor. And we are going to obtain our Ohm's law. V is equal to IR. So what does R take the expression as? Now my R becomes equal to ML divided by NaE square tau. So this becomes my R, right? My tau and 2 looks the same, so I'm going to change it. So this becomes my 2, right? NaE square tau. Now look at the right hand side of the resistance again. M, which is the mass of the electron, is a constant. It's not going to change from one conductor to another conductor. And for a given conductor, the charge density at a particular temperature is going to remain a constant, and charge on an electron is a constant, relaxation time is a constant for a given temperature. So my R becomes dependent on the length of the conductor and the area of the conductor. That means it's proportional. From here, I'm going to drag you to another equation. What am I going to say now? R is equal to L by A into the constant quantities, that is M N E square tau. Isn't that so? What is M here? ME, sorry, that's nothing but ME, which is nothing but the mass of the electron. Now, if you look at the parameters that are present within the brackets, those are going to be constant for at any point of time. For a metal, for a given, if I say I'm going to have a copper wire, irrespective of the length and area of cross section, the charge density is going to remain a constant. The average relaxation time is going to remain a constant. E and ME are going to remain a constant. So this is nothing but, yeah, I'm going to say this is proportional to L by A. This again is what you have been taught in your lower classes, that resistance is going to be proportional to the length and inversely proportional to the area of cross section. But kindly look at the quantities in the bracket. These quantities are within this. You have N, which is the charge density, which is dependent on the material of the conductor. Tau, the relaxation time, is going to be dependent on the material of the conductor. So please understand. So what we are going to do is, we are going to write this equation as some rho L by A, where what am I going to say rho as? Rho is going to be equal to Me divided by N E square tau. And what is the rho called as here? Rho is called as the resistivity of the material of the conductor. That is what we are going to call rho as. So I'm going to put up rho here, and we have R here. So you can see that we are relating the, you know, both resistance and resistivity with relaxation time. That means we can see that both resistance and resistivity are inversely proportional to the relaxation time. That means lesser the relaxation time, greater is the resistivity or the resistance offered by a conductor to the flow of electrons. Am I making it very clear, children? So what do we know now? We know that V is equal to IR. We have proved it. Where R, we are going to talk about it as ml by Na E squared tau. And we are moving into introduce resistivity rho, which is going to be Me by Ne squared tau. Now the reciprocal of resistance is called as conductance. That is going to be denoted by G. G is going to be 1 by R. Now what is this G? G is the reciprocal of resistance, which is called the conductance. So if it is going to be the reciprocal of resistance, what is going to be the SI unit? The SI unit is going to be mho. Otherwise it is simply ohm inverse, isn't it? This is going to be ohm inverse, otherwise called as mho. Is that clear? And then we have the reciprocal of resistivity, which we are going to call as conductivity sigma, which is going to be 1 by rho. And we know that rho is ohm meter, isn't it? So this will be mho meter inverse. Okay. This is what is going to be the unit. We also use Siemens to denote it. So what is this? This is reciprocal of resistivity, which is called as conductivity, right? Sigma. So reciprocal of resistivity is called as conductivity, and the unit I have written over there, which is mho meter inverse. Am I making that very, very clear, children? Now what we are going to do is we are going to try and see what is the, of course, we had this part called carbon resistors and color coding in carbon resistors, and if when the revised syllabus that had come up had actually removed carbon resistors and color coding, so I'm not going into that. The next thing I would like to do today is the relationship between J. Do you remember we did J in the previous class, children? J is current density, that is current per unit area. So I'm going to try and see if I can derive a relationship between J, E, and sigma. What is sigma? I just now told you what is sigma. Sigma is nothing but conductivity. So what am I going to do now? I'm going to try and see if I can find a relationship between J, E, and sigma. So what am I going to do? I'm going to go back and proceed with my I. What is the relationship between I and VD? I know. So let us take this as a quick recap of what we did in the class. So this is NAEVD. Now what did we write VD as? Anybody, can you pause and remember what we wrote VD as? Magnitude. Please understand we are writing only magnitude. E by M into tau. That is what is going to be my drift velocity. So what's going to happen to this now? This becomes NAE square E tau upon M. Isn't that clear, children? But what do we know? What is current density J? I by A. And what do I have here now? I have I. So I'm simply going to divide by A on both sides. So what do I have? I don't have this A now. I by A is equal to J E square E tau by M. And what is I by A? J. I'm so sorry. So we have J is equal to, what do we have here? NE square E tau upon M. Now look at this, children. What am I going to do now? What is, can we go here and see what is rho? Where is it? What is rho? Do you see rho is M upon NE square tau? So what is Ne square tau upon M, which is nothing but 1 by rho? Do you agree, children? Ne square, so let me write it like this, maybe it will be easier. Ne square tau by M into E. And I just now showed you M by Ne square tau is nothing but resistivity over here. So this is the reciprocal of resistivity. So I have 1 by rho into E. But what is rho, ma? I mean 1 by rho. 1 by rho is the reciprocal of resistivity, which is nothing but your conductivity. So what do I have now here? J is equal to sigma into E. Is that clear? Sigma is basically a scalar quantity, while current density and electric field are vector quantities. So if you want to denote it in vector form, you have to simply introduce a vector on this. This is nothing but scalar multiplication of a vector. So this gives you the relationship between current density, conductivity, and electric field. Is that clear, children? We just started off with I, and from there we went on to write I by A, and then we moved on to substitute for rho, and we simply got the relation J is equal to sigma into E. Is that clear? So we will stop with this for today's class, because from next class I will be moving into the deviation of Ohm's law and the dependence of resistance and resistivity on temperature, and we will discuss about superconductors in the next class. So this was a short class and a very short lecture for you, where we recalled Ohm's law, we derived Ohm's law, we wrote R and rho in terms of relaxation time, and then we derived the relationship between J, sigma, and E. Is that clear? So I will see you in the next class with all those which I just told you now. And so please, not much has been removed from my portion of physics. So please keep studying, keep revising. We wouldn't know what the exam is going to be like. So let us be prepared for the worst. Keep preparing, and I would like you all to stay safe. Thank you.